What's up, sports fans? Let's explore Proposition 7 together. I'm going to read through my initial statement here. It is wordy, but I still like it way better than I like the one that Euclid wrote for us. And then we'll walk through this thing here. It's a little bit clunky, so I'm going to do my best. Again, just like the last one, be ready to pause, be ready to rewatch things. I'm going to move through pretty quickly because I have it all written out already. So again, feel free to pause and stuff. So given a line segment and two other line segments extending from the endpoints of the initial line segment, if we form a triangle, then there is only one possible location for the third vertex, assuming we don't change the orientation. Okay, here's what that means. Assume that this black pen right here is my initial line segment right here, at the initial line segment. This is my given line segment that I'm referring to as the initial line segment. Now I have two other line segments extending from the endpoints. I'm going to use red pen and red pen cap as my two other endpoints. So if I form a triangle from the endpoints of this base, where this one is here, and then this end cap is here, and then eventually they meet right about there. That's where that third vertex is going to lie. The claim here is that there is only one possible location for this third vertex, assuming we don't change the orientation. So some line like this, some sort of qualifier like this is hugely important for this proof, because if we change the orientation, for instance, if I just flip-flop this real quick and I put this one on this side and this one on this side, well, then there's very clearly, oh man, this thing, that's annoying. This thing here, the third vertex is meeting all the way over here. That's a different location. So if we keep the orientation the same, then there's only one possible location that third vertex is. The first two vertices, those are fixed. Those are the endpoints of our initial segment. The third vertex is, well, wherever the red pen meets the red pen cap. So we are going to construct a proof here that if you have three fixed side lengths on some initial base, there's only one possible location for that third vertex. Now, just like Proposition 6, we're going to do one of those like, hey, pretend I'm wrong, let's see what happens. And then we end up with a kind of a crazy conclusion that doesn't make sense. This one, it's pretty involved, so I'm going to do my best. I'm going to use colors. Again, please be ready to like pause and rewind and stuff like that. This is not, more than likely, this is not the type of thing you can watch once and just get it. You're probably going to have to watch a few times if you're anything like me. I've done this one like 4 times today, so it's really fresh in my mind, and that's why I'm recording a video right now. Okay, so here we go. We're going to summarize this, but like make it make sense with our picture here. So let AB be some segment. Okay, pause. Here's AB. There's some segment AB with AC and BC meeting at point C, forming a triangle. AC and BC meet each other right here at point C. Okay, so that's our setup. We're defining our picture here. Now we're going to summarize this statement in terms of A's and B's and C's. So I'm saying, here's my claim. I haven't proved this yet. I'm claiming that AC and BC must meet at point C. There is no other option for the third vertex. I should say there's no other option for the location of the third vertex. So just like a minute ago when I had red pen cap and red pen, there was only one spot they can meet. And we are going to demonstrate that for every triangle ever. Here we go. So again, like last time, let's pretend I'm wrong. Pretend I'm wrong, and let's see what the conclusion is if I am wrong. So let's pretend I'm wrong, and there exists some point D in a different location than C, such that AC equals AD and BC equals BD. Okay, I'm going to make this one in red. So here we go. Here is some point D. This is me making an assumption. This is my like, hey, assume I'm wrong. So I just picked a random point for D. It doesn't matter where it goes as long as it looks kind of right, meaning that, hang on, let me draw this, then I'll explain. So my claim is that I drew this red triangle, DAB, such that AC and AD have the same length. AC and AD have the same length. And BC equals BD. BC, BD. Now, again, to be clear, this is not possible. I do not believe that it is possible that AC and AD are the same length at the same time as BC and BD are the same length. This is my hey, let's make this assumption and see what happens. And we're going to get some crazy conclusion showing you that this is impossible. Because ultimately, my claim is that there's no other option for the third vertex. My claim is that C is the only place that these can meet. So I'm going to see what happens. What if? What if there was another location they could meet? Let's call it point D. Well, let's connect CD, and we're going to see something kind of interesting here. It's sneaky. It's not all that complicated, but it's sneaky. So first we'll connect C and D. And I'll go ahead and do this with, how about a blue pen? And check what happens here. Now, all of a sudden, we have this triangle here, triangle CAD, triangle CAD. This triangle is interesting because it is an isosceles triangle. CA and DA have the same side lengths. Well, if this is an isosceles triangle, then by definition, angle ACD, which is this angle here, and angle ADC, this angle here, they must have the same angle measure. That's just definition of an isosceles triangle. This should feel really, really familiar because we just explored something just like this in Proposition 6, which is not a coincidence. Of course, we explored something like this right before we do something a little bit bigger. Okay, well, if that's the case, that's okay, fine. So if there exists some point D such that AD having the same length as AC and BC having the length as BD, AD and BD meet right here. If that's possible, well, then this isosceles triangle is created, and these two angles must be congruent. Okay, so far, that's not that crazy. So far, that's not that crazy. Let's keep exploring. Now, notice that CBD, triangle CBD, is also isosceles. Triangle CBD is also isosceles. Here, I'm digging for a different colored pen here. All right. So triangle CBD is also isosceles because CB and DB by design have the same side length. So that means that angle BCD, let's get that one first. BCD, that's this angle right here. So that's in green, hopefully that shows up well, is equal to angle BDC, BDC. So that's this angle here. Because it's isosceles, right? So we're saying CD is our base. We're saying that BC and BD have the same length. Okay, hopefully you have like alarm bells going off in your mind because you're like, that doesn't look right. Something is wrong. I agree wholeheartedly. So my next step here, this was brought to us by a student. This is bonkers because if angle ACD is greater than angle BCD, pause right there, let's explore. ACD, that's this blue one is bigger than this green one. There's no doubt about that. Blue is bigger than green. But this blue and this blue are the same. This green and this green are the same. So over here, blue is bigger. But then over here, green is bigger. That just can't be true. That just can't be true. An angle cannot be greater than blue and less than blue at the same time. That is ludicrous or that is bonkers. So, greater than that, then angle ADC cannot be less than that. Yes, okay, that's a summary of what I said. So therefore, because this is a false conclusion, this assumption right here, this pretend I'm wrong situation, that assumption is definitely wrong. There does not exist a point D in a different location than C such that AC equals AD and BC equals BD. So this point D does not exist. Therefore, AC and BC, as well as AD BD, they must meet at the exact same location. Again, the assumption here is that the reader recognizes or remembers, where did I put it? This right here, AC, this step right here, AC and AD, they are the same length, as well as BC equaling BD. So if you have a triangle like this, basically with 3 congruent sides, there is only one possible location for that third vertex, again, assuming we don't change the orientation. That's it. That's proposition 7. You might need to watch that again. I know it's a bit of a doozy, but again, the thing that brings this all together, and I hope that this image does it justice here, is we ended up with 2 isosceles triangles here. And in this one, the blue angle is bigger than this green angle, but the greens are the same and the blues are the same. That's the definition of isosceles triangle. So we're using a definition that's always true to demonstrate that this is not possible. It's just not possible. Blue can't be both bigger than green and smaller than green at the same time. Can't happen. There's proposition 7.